Great, welcome back everybody to numerical algebraic geometry. We will continue our discussion of witness sets a little bit more rigorously than last time. Okay, so we'll start with some polynomial system. Okay, so we have n minus m polynomials in n variables. Yeah. In other words, we're some underdetermined system as measured by m. Okay, so we're going to let x be, well, first of all, it's going to be some union of x's, k from 1 to kn. Okay, so I'm cutting out a variety with n minus m equations, and so I'm expecting possibly several components, possibly of differing dimensions, and I want to look at those of dimension m, which is the dimension you really expect to get cut out by n minus m equations, and also I want to only include those which are so-called reduced. And reduced is not a property of varieties, it's a property of varieties with respect to equations. Right? Y minus x squared cuts out a reduced parabola. Y minus x squared all squared also cuts out the same variety as parabola, but now it is not reduced with respect to that equation. Okay? And recall that the definition of being reduced is that the rank of the Jacobian at a generic point on that irreducible variety is the expected rank, i.e. Equal to the codimension of the variety. In other courses you take, this might be called being generically reduced. Okay, so for example, a parabola with an embedded point with an embedded component is still going to be generically reduced. Okay, from this, we're going to define so-called witness branch cutoff. Which just tracks all the pairs of points and linear spaces of complementary dimension to x in an incidence variety here. So this ends up being a subvariety of x in the first set of coordinates across what I was calling before grk plus 1 and then plus 1. This is, sorry. Okay, this is the set of affine M planes in affine N space. Okay. Are people okay with this being the notation for that? I'm also happy to introduce a new notation if anybody has another suggestion. Fine. Okay. Maybe if you're happier with it, just something like this would be fine. It's affine M planes in n-dimensional space. Actually, I'm going to continue with that because it's less to write. Okay, so that's the parameter space of what's going to be a parameterized polynomial system, a square parameterized polynomial system. Why? Well, what are the equations? Not that. write this as v of something. Well, we get all the f's. Well, I'm really sorry, everybody. N plus 1 minus m. Okay. There's always this back and forth you have to do. Yeah. Got my dimension in codimension. Sorry, n minus m here. Okay. N minus m dimensional planes will intersect an m dimensional variety in finitely many points. But it's cut out, an n minus m plane is cut out by m equations. Right? So what are these L's? Well, it's just some a, I, j, x, j, equal from 1 to n, plus a, I naught. It's just a generic linear form. So these aij's are all parameters. Parameters, we have our variables. Think about this as your n plus 1 times m dimensional space, where you just choose a bunch of random coefficients. Answers. Okay. Okay. That had n minus m equations. This has m equations. So this is a square parametrized polynomial system. That is exactly where we can use the parameter continuation theorem. And our conclusion is that there exists a generic number of regular points in a fiber of this projection. There's a generic number of regular points in the fiber of this projection. A generic fiber. That doesn't necessarily mean this is a branched cover. It means it's a reducible branched cover. Okay, so we don't know that this is irreducible or not upstairs. Okay. And it also doesn't mean that there's any regular points in the fiber. It just says there's some number, which is finite, and that number might be 0. Right? So now we're going to unpack some properties of this, so we can see what's really going on with this parameterized polynomial system, or in other words, this reducible branch cover. And we'll basically outline and sketch an argument for the things I claimed in the last lecture. And let's give this a name. This is the witness cover. Of the m-dimensional part of the like number of regular solutions or regular points in the preimage of a generic fiber is not 0. So the degree that's guaranteed by the parameter continuation theorem is not 0. Sketch proof. Here's a smooth point on one of the irreducible components. Okay, since x1 is reduced, if we evaluate the Jacobian, we get something of full rank. Minus. Right? This is an n minus m many rows by n matrix. Okay. Great. What happens when we choose m random linear forms to include in this polynomial system? What happens to the Jacobian? Well, for each equation we add, we're going to get a new row. And what is the gradient of the linear form?
There's just some linear equations, right?
Yeah. Yeah, so for example, like if I asked you to take the gradient of 3x plus 4y plus 5, what would it be?
So that would be dx would be what? 3, 4.
It's the coefficients of the variables, yeah.
Yeah. So I will pick out aij's.
Yeah, that's right. So what are we adding when we add m random linear forms to our system of equations? We are exactly adding m random vectors as rows to this matrix. So if this was n minus m rank, and I added m random vectors, what is the rank at the end?
N.
It's full rank.
Yeah.
It's a rank n matrix. What's another word for that having rank n? Invertible. But in terms of characterizing what the solution x
Regular.
comma l is, it means it's a regular one. So there's at least one fiber with at least one regular solution. Right? Remember, this was the definition of the generic count in the parameter continuation theorem. It was the supremum of all the counts of regular solutions. And so since we showed that at least one of these is one, we show that this is at least one. Okay. So if I pick a generic point down here, I will have a regular point of the fiber. In other words, this is dominant, essentially certain. Okay. Great. Claim 2, sorry, claim 1, that was claim 2. Before we get to that. So what was this? The story was that as long as I pick linear forms, which go through X, in such a way that none of the hyperplanes cut up by those linear forms contain the tangent space of X at X, then this system will be full rank here, right? So the problem occurs exactly when I choose a linear form, which is tangent to my variety at that point. In other words, it's already in the row space of the Jacobian. And so it doesn't bump up the rank. So I have some Jacobian here, and the row space there describes the tangent space. So if I take something that's already in the tangent space, and I throw it in, then I'm not upping the rank. Okay? So in other words, if a hyperplane doesn't contain the tangent space of a variety at a point, then that hyperplane is said to be transverse. Okay, so for example, if we had a curve, we choose a point, the tangent space, some line through that point, any hyperplane containing that dotted line would be said to not be transverse to the curve. If a hyperplane not containing this dotted line, sorry, not containing the dotted line is transverse. Containing the dotted line, not transverse. So all we said in the claim 0 is that if you pick a smooth point on a variety, you can choose hyperplanes which are not transverse to the tangent space. Sorry, which are transverse to the tangent space. I don't know why I'm mixing that up. Transverse means like not tangent. Okay. And you can extend this definition to just a linear space. Okay. And now a fact, let's say, generic linear space of complementary dimension x I is transverse at each point of intersection. This is stronger than what we had just shown in claim 0, and I don't want to prove it. So claim 0 said if you pick a smooth point on the irreducible variety and you choose a random linear space of complementary dimension through it, it will be transverse at that point. We have said nothing about guaranteeing transversality at other points of the intersection. So a priori, you might think, oh, well, maybe no matter what linear space I choose through here, even though most will be transverse here, maybe all of them are not transverse somewhere else. And this fact says that's not the case. A generic linear space will not be tangent to the variety at all. And that should vibe with all of your intuition. You draw a curve, somebody randomly draws a line, it is not tangent to that curve anywhere. Okay. But giving this fact will save a lot of time. Back to this branch. Claim 1 is remember that X has components xj of dimension n that are all reduced. And this is just a set theoretically. So how do you earn membership into this set? Well, you have to be a point on big X, and you have to be a point on the linear space. Well, if you're a point on big X, you can be a point on any of these. Right? So that's the same as saying that I'm a point on one of these components in the linear space. Okay. So that's just a set theoretic argument. Pretty immediate. Second one. Each wxj is irreducible. So wx collects all the incidences of points on your variety intersected with complementary linear spaces. wxj is focused on one particular component of the correct dimension, which is reduced. Okay. So now we got this wxj going down to our set of linear spaces of dimension n minus m in dimension n. And this fact I said that almost all linear spaces aren't tangent anywhere to xj. Tells us that there is some subvariety proper of linear spaces which are. Okay. This will be part of the exceptional set of this. Okay. Upstairs, you earn membership in the exceptional set because somewhere upstairs you have that linear space. And then you have the point in which it's tangent to. Right? Because that's the solution which is not regular, that should have been. It earns multiplicity. In the same way that you learn in calculus, you take a secant line to a curve, you have these 2 points, but then you take a limit, and those 2 points collide. So you really think about that intersection point as one point with multiplicity. Same thing's going on here. But this might look different. It just projects down to the red locus downstairs. And now I want to claim that this thing's irreducible. And interestingly enough, we have developed almost no tools for showing that a variety is irreducible in this class. Because I'm avoiding talking about prime ideals, I'm avoiding a lot of algebraic geometry in this class. That's a feature. But there is one result about irreducibility that we did earn in our monodromy chapter. That being irreducible upstairs here corresponds to a group theoretic property of the monodromy. What was it? Transitivity. Yeah. So in other words, if I can show, okay, so I have a bunch of points in the fiber here. If I can show that there exists a loop downstairs, which could take any x1 to any x2 in this fiber, I would show transitivity, and I'd be done. Okay?
Yeah.
Okay. So what will we do? So this is wxj, and then somewhere we have actual xj. And these are different, because this is a variety and this is a variety with a bunch of linear spaces. It's an incidence. Okay. So this is our L, which in this picture looks like this, L, right? And we have a bunch of points in the intersection of xj and L. Many of these are non-real in my Blackboard picture. Okay. We're gonna call this one x1 and this one x2. And if you'd like, actually, let's think about this as a surface. Okay, so now the optical illusion of my fantastic artistry suggests that that's a surface on the blackboard. And yeah, maybe it's even like singular at some places, okay? These are not two components, that's just one thing. Great, whatever. So there's maybe some singular locus here. Maybe it's like pinched along this line even, I don't know. Okay. But we have this result that varieties are connected amongst their smooth limits. In other words, the singular points on a variety is a proper subvariety. Okay. Which means that there exists some path in this variety, let's call it tau, which sends, let's do it the other way, x1 to x2. So tau is a path from 0, 1 to xj. Tau of 0 is x1, tau of 1 is x2. Okay. And not only that, it's this in the smooth. It's really a smooth path. All right. So at the beginning, I have a line which is transverse through x1. Okay. Now, all you got to convince yourself of is that as I move along this path in the movie, where x1 becomes x2, that I can move this linear space of complementary dimension continuously in such a way that it remains transverse the whole time. And to convince yourself of doing that along this point, you can just take the orthogonal complement of the tangent space, and that will remain transverse the whole time. Right, so you imagine like stabbing the surface with a really long toothpick, and you're moving it in such a way that the toothpick is never tangent to the point you're intersecting.
So if I understand it correctly, I'm moving around from x1 to x2 along T.
Yeah.
But when I move x1, like if I slide x1 along tau to x2, the line L will also move smoothly, right?
You want to be able to choose it so that it can.
And that can happen given that there is a path which can avoid that singular point, singular locus, right?
So we already got the path that avoids a singular locus.
Mm.
The comment that you can also choose in conjunction, right, simultaneously, a path of linear spaces that remain transverse is going to tell you that this path tau gives you a path up here.
Why can I do that? Why am I allowed to?
Say this is x1. Okay. So let's just say this. So, and my path tau is this.
Oh, so I'm just choosing the, okay.
So every point along the way, I'll just take this line, and that's how.
I see. Just take the normal essentially, you mean?
Yeah, so this actually doesn't work.
Okay.
Right, so I'm suggesting this, but you should see why this doesn't work. So let's take it, right? So let's take this line and imagine moving it in a normal way.
Okay.
Immediately right here, I have a problem.
So I'm not allowed to be tangent
Anywhere.
Okay.
Okay.
It's okay, but there's only one point, one line which is tangent, so I can just choose.
That's right.
Okay.
Yeah, and so this is a loose argument that I do not want to make rigorous for the sake of this course again, but I do want to sketch what's going on. What's going on is one needs to make an argument that in order to follow along this path, so that as soon as you have a smooth path like this, you can choose a linear space which avoids this red locus here along the way.
Which is exactly the tangent at that point.
Down here is the space of all linear spaces of complementary dimensions, which are tangent to some point.
To some point, okay.
On the variety, yeah. if you believe you can choose this, I believe you can. Then you will believe that essentially from every t, you're getting some LT, right? So you got this map, let's call it, I don't know, rho, okay? And then tau cross rho is a map into the incidence variety. Okay, so from taking a path on the variety, you can cook off a path on the incidence variety as long as you're choosing L's to go along with your path along the way in a nice way. And as long as you convince yourself you can do that without making anything tangent, this shows you probably can't do that over the real numbers, but that is a feature we've seen throughout the course. You can do it over the complex. Then that will be the path, which will then project down to a loop, which will move x1 to x2.
And the reason why we can't do that over real numbers is because it is not path connected or something.
Yeah, so what happens over reals? So what happens over reals is codimension 1 spaces over the reals will decompose the space into connected components, right? And so what could happen is that you might have something like this, where you have all these connected components. They look like chambers in the complement of this exceptional set. And maybe the only path you can take upstairs actually does have to go really far away, which would mean downstairs it would have to cross here. So that's the issue. Okay. So that is a sketch of how one might geometrically prove that this incidence variety is irreducible. The incidence variety is not the variety, but from paths on the variety, if you can convince yourself, you can pair it up with paths of linear spaces in a nice way, then you'll earn transitivity by explicitly exhibiting a monodromy element which moves x1 to x2. If you have algebraic geometry background, the easier way to do it is look at the projection onto the space of xj and look at the fiber over that.
And that projection is dominant. Maybe that's why it works.
Yes, for every point on the variety, you can find a linear space through it. And in fact, all the linear spaces through that variety kind of look the same. And they're all irreducible, all those fibers. It's not a finite to one map in the other direction, but your fibers all look exactly the same. Your downstairs is irreducible, your fibers are irreducible, and so you can conclude the space upstairs is irreducible. But this is a monodromy argument, which requires only perhaps a little bit of faith with this this row map. Okay. Great. Almost there. So claim 0, you at least have some regular points of the fiber. Claim 1, Wx is the union of the Wxj's. This is the union of the Wxj's. Number. And these are all irreducible. Okay. Claim. The monodromy can be generated by transpositions. Let's try this again. Let's just look at one component here. Fine. And then we have some this here. Great. Good. regular point, call it L, and a random line through it. I can restrict this branch cover to the preimage of this line through L. This point, which itself is a linear space, this line, which maybe I'll call script L, and this you think of as just a copy of C minus some points. And upstairs, so I'm restricting this cover to a random line downstairs. Okay. And so in our monodromy section, we talked about a theorem of Zariski, which says that if I do perform this restriction, then the fundamental group of this surjects onto the fundamental group of this space. So this is like this logical result, conclusion, it's topological conclusion. But what it essentially said amongst numerical algebraic geometers is I can restrict to a random line in my parameter space and I won't change the monodromy group. Okay, I will not change the monodromy group. Okay. Well, what's going on in the picture of xj? So yeah, here is my point L. So this line here is a point in my parameter space. And then I might have many points on the lowercase l, which correspond to, I don't know, say many parallel lines, for example. So this is like a line of lines, right? Little l is a line of lines. Now I've drawn them, little l is a line of linear spaces. Now I've drawn them in a parallel way, but you can think about them however you want. It's a pencil of linear spaces. And now the thing I would like you to convince yourself of and take on faith is that, okay, so as you sweep through this family, yeah, you're going to be tangent in some places, right? So you can imagine that movie of that line sliding down the variety. You become tangent, you become tangent, you become not tangent, you become tangent. And the places where you become tangent are exactly these intersection points. Right? So as I'm moving along this line, tangency happens exactly when I'm on this exceptional set downstairs of the witness cover. I want you to convince yourself that when that happens, you're only tangent at one point. You're not a bitangent. Okay, so maybe I picked a really bad line, and I do have a bitangent. But remember, I'm picking a random line and a random line, a random linear space and a random line of linear spaces containing it. Okay, so all I would have to do if you complained about this is wiggle my L a little bit and do it again.
So I mean the points where the bitangency happens is a proper contained in a proper subvariety.
Yes.
What-
Yeah,
what
equivalently
is-
that, yeah, thank you, Prabhu. That's another thing you can convince yourself of. So the red is where all the linear spaces which are tangent to xj.
So the intersection of.
So let's mark all the places where it's not just tangent once, but tangent twice. Okay, and we'll call that, we'll mark those with triangles. Convince yourself that that's a proper subvariety of this. Okay, and then you'll also know that a random line won't hit it. Okay. So that's what I ask for you to take on faith here, to be able to conclude claim 3. Okay. Why? Upstairs at a generic point, you'll have D points. But our argument just now said that here you have d minus 2 regular points, but then this one which comes with multiplicity 2. Right? Which means if I just look really locally around here, the only 2 points that could possibly come together are these two. Everything else is separated. So the only monodromy that can happen around this point is a transposition. Right? So in your homework for the monodromy section, you actually compute these monodromy loops around single points outside of your parameter space. Right? And so my claim is that as long as at that point, only 2 points come together, the only candidates for monodromy locally here are transpositions. And we also know, so now we know that the monodromy group didn't change. The monodromy group is generated by itty bitty loops around these intersection points. Those can only be transpositions, and the monodromy group is transitive. I told you the only transitive subgroup of Sn generated by transpositions is Sn. So this is some symmetric. It's a symmetric group on the number of points in the file. So definitely some geometric facts that we've used along the way that have been very hand-moved. If you're really interested in seeing any of these proven, talk to me and I can write something up. But the big picture here. You have a variety, you can cook up a square polynomial system, which is parameterized. You apply parameter continuation theorem. You argue that there's at least 1 point upstairs. Okay, that tells you that this is a dominant map, so you have a reducible branch cover. Okay. Now, how reducible is it? Well, we know that Wx will be the union of Wxi xj's, and that each of these is irreducible. So this decomposition exactly tells you how reducible this incidence product is. Okay. All right, great. Now you do what you always do when you have a reducible branch cover, which is you just focus on one of the irreducible components upstairs. Okay. And if you do that, you find out that the branch cover is pretty much as boring as possible from a monodromy group point of view. It's got the full symmetric monodromy group. So if you have a reducible branch cover, then you can understand what happens monodromy wise by understanding what happens on every irreducible part of that reducible branch cover. The monodromy group as a permutation group is just a direct product of the monodromy groups of all the restrictions to the irreducible parts. This is what you expect. Right? I take a linear section of this union of two varieties, I can't hop around from the circle to the parabola or back and forth. Corollary, the monodermic group of a witness cover is a product of symmetric groups. One for every component of the variety of that dimension, which is reduced. And how big? Well, each one of those irreducible branch covers gets their own degree. The DI is the degree of the axon. Interestingly, this is actually your definition of the degree. So the degree of a variety is the generic number of points of intersection with a linear space of complementary dimension. But we earned that pretty much entirely through this theory of branch covers and using the parameter continuation theorem to get that as a well-defined thing for an affine variety. And it does agree with your other ideas of what the degree of a variety would be, degree of a projective variety, perhaps. You would just take the projective closure. All perhaps a little bit long-winded way of saying that if you slice a union of varieties all at the same dimension and you wiggle around that slice, you have to stay on the variety you're on, the irreducible component that you're on, and you can move them around any way you want, just by wiggling around the linear spaces. Perhaps pretty surprising. Okay. So who cares, right? Numerical algebraic geometry class, I'm gonna want this to correspond to some algorithm somewhere, something that I can actually use, right? So back to witness sets. So witness set still triple. Equations which cut out x as a reduced irreducible component. L, a generic linear space of complementary dimension. S, a collection of numerical approximations for all the points in that intersection. Okay. And I kill irreducible here, but I replace it with with x being the union of reduced irreducible components of the same dimension, then the definition of witness set doesn't change. I still get to take some f. I want to cut out x as a union of reduced components. Okay, my linear space I can just choose one because all the xj's are the same dimension. I don't have to like fumble around with linear spaces of different dimension, and then I can take a bunch of numerical approximations. So a witness set for this union will still be drawn like this. The data here is exactly a fiber here. Okay. This picture here is a fiber of this map. What is all the data contained in a fiber? Well, as soon as you have a fiber, you know the linear space you're cutting with, so that's your L. You already wrote down equations for this, so that's your F. And then the first parts of all the points in the fiber are your S. Okay. These pictures are the same. So let's get an algorithm. Somebody gives you a witness set like this picture. That's the input. Out. A witness set for each of the components. That's the algorithm I want. Sure, I can write down equations. I can pick a parameter downstairs. I can solve it. That's parameter continuation. We've done that. That's old news. That's 2 sections ago.
Yeah.
I get a bunch of points, so I have a witness set for a reducible variety. Possibly reducible, possibly irreducible. I have no idea. How am I going to tell which components are in this slice? Right? That's the big question. This answers that question. Okay. So the name of this algorithm is called the monodromy breakup algorithm. I think would be a really great math lesson. Okay. Compute monodromy elements of I. I'm going to go on a bunch of loops. Loop-de-loop-de-loop. All over and over and over and over again. Okay. Along the way, partition S. S is your points in the witness set. Into orbits of G. Maybe I'll give these orbits names. S1 through 1 to some K. So we're like, look, there's 4 points in this intersection. Let's do a loop. Okay. So 1, 2, 3, 4. And I see, oh, when I did this loop, 2 and 3 swapped places. So those must be together in an orbit of the monodromy group.
Mm.
And so they must be points on the same component. Okay. And so after I do this loop and I see 2 and 3 swap, I go, okay. Instead of having no idea anything about these points, I now know that 2 and 3 belong together. And I have no idea what's going on with 3 and 4. So I refined, 1 and 4. So I refined this set partition. Okay, so I'm going to keep on breaking up my solution set into orbits.
What's the stopping criterion?
As you just stop refining. Heuristic. So remember, we're never gonna have any chance of understanding the discriminant. We're not gonna really be able to pick out the right loops, but we know it's super duper complicated. And so we don't expect a lot of loops to be necessary to essentially generate each of these individual monodromy loops. Right? So we don't expect this to take very long. And we're actually gonna code it. Okay? And eventually you output the set, well, F doesn't change, L doesn't change, and now you just got the SIs. Okay. That's monodromy breakup. And so if you're gonna understand witness sets and how to go from polynomial system solving to actually being able to construct witness sets for irreducible varieties, which is like really the fundamental object here, you need to understand monodromy. But okay, then we will stop this part of the class and we will continue in 5 minutes. I will do a little bit more board work. I'll tell you what the trace test is, and then we will code both monodromy breakup and the trace test in the second part of today's lecture. Thank you.